Hey there, STEM Chemistry. This is Miss Ruark. This is podcast 8.3, and we're talking about phase changes. Now, some of you had questions about the phase diagram, so we're going to get into that a little bit more in this, and we'll do some more work with it during this unit. All right, so phase diagram. So phase diagram is going to be a graphical way to summarize the conditions under which equilibrium exists at different or between different states of matter. Okay, so why are we talking about phase changes again now? Well, because phase changes are going to be governed by intermolecular forces, and that's what we've been talking about for a while. All right, so phase changes are ways to predict the phase of a substance at a given temperature or pressure. Okay, so what do we mean by the equilibrium? Well, the equilibrium means that on this phase diagram, we're going to be able to determine what temperature and pressure combination will give us an equilibrium between solid and liquid, or solid and gas, or liquid and gas phases. An equilibrium just means that there is there's a forward and a reverse reaction happening, or a forward and reverse phase change happening that will end up keeping the melting process going on at the same time that the freezing process is going on. Okay, we'll make sense of this in just a second. All right, so here's a phase diagram. You've seen this before, and let's just make sense of some of the stuff that's on here. All right, so this line right here, this would be the equilibrium line between, I can't draw. Sorry, this is the equilibrium line between the solids and the liquids. Okay, so this is the equilibrium line between solids and liquids. If we were to increase the temperature, we would be able to force more solids to turn into liquids, which we would call melting. Well, if we were to decrease the temperature, we could force more liquids to change back into solids, which would be freezing. Okay, this right here is the equilibrium line between solids and gases. Okay, so this would be the melting point line, and this would be the boiling point line. If we were to increase the temperature just a little, or if we were to decrease the pressure just a little, we would be able to force the substance to change into a gas, which would then make it it would be the boiling change. Okay, at the triple point. The triple point is where all three of the phases are in equilibrium, so conditions are favorable for all three to exist. There's only one given temperature and pressure for any substance so that there's a triple point. So a triple point will only exist at one given pressure and temperature for any substance. It cannot be at multiple places. Let's see, what else do we have? The critical point. Okay, so the critical point here, this is the temperature and pressure, the critical point, at which beyond this critical point, you can no longer have a liquid phase. It's simply just going to be a gas, because you can't distinguish the liquid from the gas. So it's just a gas phase. All right, so interpreting this phase diagram, the critical temperature is the highest temperature at which a distinct liquid phase can be formed, and you can distinguish it. Okay, at the critical pressure, this is all the critical point, is the pressure required to bring about liquefaction of this critical temperature. So it's the highest temperature that tells us how much pressure is needed in order to keep it a liquid. Okay. With this, non-polar and or low molar mass substances have lower values for critical temperature and pressure, which kind of makes sense because they pull apart easily to change into the gas phase, because the non-polar substances don't have that polarity there, that electrostatic attraction holding them together. Okay, so we need to talk about vapor pressure here too, because vapor pressure is real important in this phase diagram, because we're changing from a liquid to a gas, right? From a gas to a liquid. So vapor pressure, we talked about it during the gas laws, is the pressure exerted by a vapor in the space directly above a liquid. Okay, we also said, we've talked about intermolecular forces, and guess what? If we have a higher intermolecular force, it's going to have a lower vapor pressure, and that's because these don't easily change. Higher intermolecular force means that they want to stay together. They don't want to change into the gaseous phase, and since they're not changing into the gaseous phase as easily, there's not going to be as much vapor sitting above the liquid, and so the vapor pressure will be lower. All right, so this will create what we call a dynamic equilibrium. And a dynamic equilibrium just means that the rates of changing from from liquid to gas and gas to liquid would be the same. Okay, equilibrium meaning that what one is doing, the other one is doing opposite at the same time at the same rate. All right, well, we have these things called volatile liquids, and volatile liquids are substances which it says substances with higher vapor pressure allow liquids to evaporate to dryness. So what does that mean? Well, it means that there is no dynamic equilibrium. The liquids will just evaporate quickly into the gaseous phase, and there is no going back to liquid. So they prefer to remain in the gaseous phase and will not come back down to the liquid phase on their own. You actually have to force them. Yeah, it's not good. Okay. Boiling. All right, so we talked about boiling when liquid goes to a gas. So liquids will only boil if the liquids can change to gases and escape the container which they're in. And so liquids will boil when the vapor pressure equals to the atmospheric pressure that acts on the surface of the liquid. We talked about this in the gas laws a little bit. So bubbles of vapor form within the interior of the liquid when it's boiling. When it's boiling. When it's evaporating, the bubbles of vapor or gas form at the surface of the liquid. And, well, I didn't mean to have this in here for you. Sorry. We don't want this. We're not doing that. Okay. But the lower the vapor pressure, the lower the boiling point. That's what I wanted you to get out of this. We're not going to do Clausius-Clapeyron calculations here, but you might do them later. Okay, so lower pressure equals a lower boiling point. So hopefully that makes a little bit more sense with that phase diagram, and then we'll be able to use the phase diagram. We're going to do some practice with it and how to read it and how to get information from it with the pressures and the temperatures during this unit. Okay, I think that's it for today. I'll see you later.